Okay, good evening, everyone. Welcome to O-level physics lesson on electromagnetism. Today will be our last lesson on electromagnetism before we go to our last topic. My name is Mr. Chu. Today is Tuesday, 16th of August, 2022. Okay, so for last week, we went through question on the basic concept of electromagnetism. Okay, so how magnetism and current can produce a force. Okay, basically is how a magnet plus a current can result in a force. But before that, you also learned that a current actually produce magnetism. Okay, then the second part will be when you bring a current and a magnetism together that is not in the same direction, it will produce a force. And this idea came about this new invention called the motor. Okay, in the past, it may not be easy to make things move, to make things turn. Okay, but after we know that current and magnetism can produce a force, that is how a motor is born. Okay, so if we can just produce, if we have any electrical source, and then you arrange with some magnet, it can actually produce a force, and then things can turn, things can move, and therefore a lot of invention came out after that, and that is why this topic is very important. Okay, so I repeat one more time. For this topic, first, we realize that every current will produce a magnetic field. Okay, current produce a magnetic field. And because of difference in magnetic field interference, it resulted in a force. What do I mean by that? When you have a current in a magnetic field environment, there will be some interaction between the magnetism, am I right? And because of that, it results in a force. Because you all learned before, light pole repel, unlike pole attract. So when you have a current that is placed in a position, in a location with magnetism, the current produce some magnetism, am I right? The magnetism will cut into the existing magnetism, and that result in a push or a pull motion. And that is why there's a force. Is that clear? Okay, and that is why we learn there's this invention, this wonderful invention called motor. And therefore, you all got things like car, you got things like fan. Okay, without this idea, there'll be no car, there'll be no fan, you'll be walking to school, there'll be no fan in school, teacher will be using the blackboard to teach you all. Okay, however, you'll have no physics lesson because it's not being taught. Okay, so let's start with the first lesson. Sorry, not first lesson. Let's start with the first question. Okay, all of you look at question number 37. Okay, 37, take a look. Quickly tell me, what rule do you use? Okay, very good, Yu Ting. Very good, Xiao Xing. Yu Ting, you got it correct. Okay, I asked a question. This question uses what rule? Okay, what rule? And before that, Ryan asked me a question. Is the magnetic interference known as magnetic flux linkage? Where do you heard of this, Ryan? Okay, what you are saying actually is correct. So Ryan, where do you heard of this word, magnetic flux linkage? Okay, but all of you do not need to know this thing called magnetic flux linkage. Besides Ryan's school teacher teaching him magnetic flux linkage, did the rest of the school teacher teach you this term? Okay, so far only Yuting got this correct. How about the rest of you? What should be the answer for this? I also try myself using my left hand. Okay, Oscar, well done. Okay, Chelsea, well done, well done. Okay, how about left with Ryan Howray? Okay, Ryan Howray and Bei Kwan, what's your answer for 37? Okay, my first question to you all is what rule do you all use? And then only Yuting and Xiaoxing tell me the answer. Okay, so for this question, you need to use the Fleming. You don't need to remember his name lah, but it actually belongs to him. Okay, Fleming left hand rule. Okay, so all of you need to use the Fleming left hand rule, and then you all learned before. Okay, your thumb, index, and middle finger is equivalent to FMC. Okay, so based on this, Ryan, can you try again? Okay, so can you see from the current here, on the left side, this is the current. Okay, this will be your index, sorry, your middle finger. Okay, Ryan, on the left side over here, okay, on the left side over here, this is your middle finger because it's current. Okay, and then from north to south, this is your magnetism, which is your index finger. Okay, so you position your index finger from north to south, your current, okay, your current in this direction, then your left thumb will be pointing down or up. Okay, your left thumb will be pointing down or up. Ryan just left the class. How are you, Bei Kwan? Can you do this question? How Ray and Bei Kwan are both of you there? Ryan, welcome back. Your second answer is correct. Okay, Bei Kwan, okay, on the left side here, where the car is moving from the eye into the paper. This is your current. Okay, your current, can you let your left middle finger be the current? Then from north to south, can you let your left index finger be the magnetism? And then from there, can you tell me your thumb is pointing up or down? Okay, Bei Kwan, can you tell me your thumb is pointing up or down? Okay, then for Hao Rui, are you there? Are you there, Hao Rui? Hao Rui, are you there? Ryan, do you understand now? Oscar and Yuting, can remove your reaction for now. Hao Rui, Bei Kwan. So Bei Kwan, if you put your middle finger here and your left index finger here, where would your thumb be facing? Good. Okay, so on the left side, the force is going down. Okay, then on the right side, it's the opposite because current is in opposite direction. You'll be going up. So in this kind of thing, is it turning based on your eye? Is it turning? Which direction is it? This direction, am I right? So this is clockwise or counterclockwise? Bei Kuan. Hao Rui, can you tell me, are you here? Before I go and call your house. I'm going to count to 5. Hao Rui, give me some response before I call you. 5, 4, 3, 2. Okay, Hao Rui is not here. And he just left the class. Okay, Bei Kuan, can you tell me? The left side count goes down, the right side goes up. Is it clockwise or anti-clockwise? Okay, so correct. Bei Kuan, you're right. So are you able to understand? It will be it will be anti-clockwise. Okay, so answer will be either A or B. Okay, but in this case, will it turn all the way to the other side or will it turn halfway and stop there? Okay, you only turn halfway, because once, okay, it is halfway here. Okay, one is halfway here. At the bottom, okay, let me show you. This is north and this is south. Okay, this is the eye view. When you reach a point where this part is going away, going away will be like this. Coming in is like this. Am I right? It turns to here and it turns to here. So in this case, it is going in and in this part is going out. Okay, so let me erase the part. Okay, can you see now? Let me erase this. So when it becomes like this, what happened? What happened? Okay, the magnetism is still going from north to south. Okay, so when you reach this point, okay, the force will be going up here. The force here will be going down. Okay, and these two forces will cancel out each other and then they'll remain at this point. Okay, so therefore you only turn 90 degrees. Okay, but in real life, it will not turn 90 degrees. In real life, it will overshot a bit, then come back. Understand? Because it will not jam brake exactly at 90 degrees. Okay, but you rest in this position. Okay, so for this question, the answer will be A. Okay, everybody clear? Hao Rui, are you able to do this question? If all of you understand this, give me a thumbs up. Thank you, Xiaoxing, Oscar, Yuting, and Ryan, and Bei Kuan, and Hao Rui. And Hao Rui, Bei Kuan, and Ryan, can the three of you on your camera? Okay, this will be my last reminder today. I don't need to remind you again. Ryan, on your camera, don't tell me the toilet again. Okay, let's do question number 37. Ryan, please on your camera. Okay, this is another moto lighting. Okay, you can just start doing this. Start doing this. You may begin. While I get some drink. Okay, start. Okay, Oscar, well done. Yiting, well done. Chelsea, try again. Okay, Howard, well done. Chelsea, well done. Okay, left with Fei Kwan and Ryan. Ryan, well done. Okay, Fei Kwan, are you there? Fei Kwan, do you need help? Fei Kwan incorrect. Okay, so what happened here is the axle is the pivot. Am I right? And then in this case, current flow this way. So current flow this way and come back. Correct? So let me use the left hand rule. Magnetic field, current. Okay. So the force, okay, you come in check. The force on the left side is coming down, on the right side is coming up. Clear so far? Okay, so what are the different scenario? So you can see that if I look from here, if I look from this direction, if I look from here, right, you will see the circle, correct? Then you will see this thing going there and so on. And then there's a North Pole and a South Pole. Okay. Hold on. If I look perpendicular to the thing, you will look. Okay, hold on. Okay, at first it will look like this. Current, then it will go in, and then here it come out. So this is the North Pole, and this is the South Pole. Then as it turn, okay, as it turn, like this, clear? This is the going in, this is coming out. The South Pole and the North Pole are the same. Okay, can everybody hear me? If you can hear me, raise your hand. Ryan, everybody can hear me. You check your speaker. Hold on. Okay, Ryan can hear me already. Okay, so if the force, let's assume that the force are the same. Okay, the force are the same. Okay, the force are the same. Clear so far? This is what happened. So why is it that when it start turning, okay, when it start turning, the moment decreases? Why does the moment decreases? That's my question. Okay, remember I told you all, the center here is the pivot. Okay, the center here is the pivot. So I'm going to draw the perpendicular distance. Okay, so this is the perpendicular distance. Okay, but for the second one, this is the perpendicular distance. Can you see? So D1 and D2. So D1 is more than D2. So moment 1 will be more than moment 2. Is that clear? Okay, why? Because the formula of the moment is FD1 and FD2. Let's assume that the both F are the same. Okay, but because the distance is now reduced, so the moment is reduced. Are you all clear about this? Okay, if you are very clear about this, give me a clap reaction. Okay, all okay? How Ray, are you okay? You all understand this perfectly well? Okay, one of you mentioned C, the forces on the two other sides of the coin start to produce a moment. Okay, number C, the answer doesn't make sense at all. It doesn't explain anything at all. Okay, so but basically what happened is this. As the thing rotate, as it rotate, can you see as it rotate, the perpendicular distance decreases, assuming that the force are still the same because of the lower perpendicular distance. Okay, because the distance go down, so the distance go down, the moment will go down as well. All right, so this is what this question is doing. Okay, is it difficult to you? Okay, let's continue. Next question. All right. Okay, let's do question A, part 1 first. Okay, all of you try doing A, part 1. Okay, 2 mark question. You don't take more than 2-3 minutes. Yiting, your first part is correct, but you need to explain a bit more. Based on this, I'll just give you 1 mark. You must tell me, left side go, the force is up or down, right side up or down. Okay, Oscar, I'll give you 2 marks. You can improve a bit more. If you mention that left side, the force go up or down. But based on your direction, I will not fault you. You're actually correct. Ryan, let me read your question answer. Okay, let me read Ryan's answer. Okay, Ryan is wrong. Can you see this question and the earlier question? The direction of the battery is different. So can you try again? I'll give you, I don't know whether should I even give you 1 mark. Okay, but there's only one thing that's not correct. Okay, Ryan, you try again. Okay, how Ray, you're describing the Fleming left-hand rule. That one don't need to explain. Don't need to explain. Left finger represent what? Left thumb represent what? That one don't need to don't need to elaborate. Okay, how Ray, I'll give you 2 marks. Okay, I'll give you 2 marks for your answer. Okay, Chelsea, well done. Yu Ting, why your oh, let me see. sorry, I see wrongly. Yu Ting, you are explaining further, is it? Okay, then Yu Ting, you add on that, you'll get correct. Well done, well done. Okay, have everybody answer me? Where is Bei Kwan? Bei Kwan, where's your answer? Okay, left with Bei Kwan. So let me share with you how I can explain this. So first of all, I must say that, hold on. Okay, the first part you understand about this, when there is current in the magnetic field, a force is produced. Okay, then you need to explain further. So you can write down by Fleming's left hand rule. Okay, the force produced on the left side is downwards, and on the right side is upwards. Thus, the coil will turn clockwise. Is that okay? Okay, Bei Kwan, why are you not replying? Hey, Bei Kwan, can you show me? Are you there? If you are there, give me a yes reaction. Okay, Bei Kwan, you need help. I already given you the answer for part one. Do you understand part one? Okay, Kwan, can you type out the answer and show me? Okay, let's move on to the next one. Okay, all of you do part two. Part two. Okay, Kwan, can you give me the answer for part one? Okay, thank you, Wei Kwan. All right, so now after it turned 180 degree, why does it continue to turn in the same direction? 2 marks. Okay, how very well done. Yuting, you can improve your answer a bit more. Oscar, you can elaborate a bit more. Okay, because when you say 180 degree, it's not correct. Okay, so I know that this split ring communicator will actually change the direction of your current every 180 degree. Okay, that is not wrong, but you need to be a bit clearer at which point it will change direction. So let's say in this picture, this is the starting point. Okay, this is the starting point. Okay, this is the starting point. So at which point will it change direction? Okay, so let me give you a clue. How do I start this? I will say things like after a 90 degree rotation. Okay, don't need to write clockwise or anti-clockwise, because if the first part you write wrong, here you also will be wrong. Just write after 90 degree rotation. Okay, what happened is the split ring commutator, okay, will reverse the direction of the current in the coil. Okay, not in the circuit, but only in the coil. Is that clear so far? Okay, so after a 90 degree rotation, the split ring commutator will reverse the direction of the current in the coil. So this causes the force acting on the coil to reverse direction as well, and ensures that the force on the left side is always downwards, and the force on the right side of the coil is always upwards. Is that clear? Okay, so can you look at your own answer and then you see, can all of you just tell me which part you can improve? Just type out the part you can improve based on what you have written so far. And then I mentioned after 90 degree rotation, because the diagram is vertical. So after a 90 degree rotation, then the split ring commutator will cause the current to reverse. And because on the right side is going down, when you reach 90 degree, after 90 degree, you actually change to up. So on the left side is always moving up. Can you all see that? Okay, so can you all look at your answer and then tell me the part that you can improve your part of the answer? Then we'll move on to the next question. Hey, hold on. Is the left side always downwards? Okay, I'm sorry. If it's okay, I made a mistake here. So the force on the left side is not downwards, it's actually upwards. Am I right? It's upwards. And then on the right side is always downwards. Correct? Okay. Can you all check whether am I right or wrong? Okay, Yuting, well done. Okay, sorry, can you all also check for me? Left side is upwards, okay, left side is upwards, right side is downwards. So my answer is actually incorrect for both. Left side should be upwards, so therefore it will turn clockwise. So therefore it will turn clockwise. Okay, Haori asked me a question. Why is the purpose of the split ring commutator to reverse direction of the current every half revolution, but in reality it changes every 90 degrees? In reality, it changes every 180 degrees. Is that clear? Can you see? There's a gap at 180 degrees. So this, okay, wait. So let me try to zoom in and try to explain to you all. Okay, so just let me highlight this part. So can you see on the right side? Okay, this is the right side of the commutator. So current move in this way. Okay, so it start at the middle. They start at the middle of the commutator. So as the thing turns clockwise, means that it's turning this way, right? Turning this way. So can you see? From here to here is only 90 degrees. So after it reach the gap, you reverse direction, and then the other side here, this part here, this other side, will actually receive the positive current for another 180 degrees. And then you'll repeat every 180 degrees. Harry, do you understand this? If you understand what I mean, say yes. If you're still confused, say no. Then I'll try to explain again in another manner. Okay, how do you understand? It's not 90 degrees. Just that from this starting position, it only takes 90 degrees to change direction. Okay, it's because of this starting position, it only takes 90 degrees to change direction. Then subsequently, you only change direction every 180 degrees. Okay, how are you are clear now? All right. So everybody okay with this question? Okay, let's continue. Let's look at part B. Okay, so this figure shows how the moment acting on the coil depends on time. Okay, we're talking about moment versus time. So on figure 8.2, mark with the letter H, where the coil is horizontal. Okay, basically, this is your north, this is your south. Okay, this is your split ring communicator. So basically, your thing is here. Okay. So at which part of this graph would where the coil is horizontal? Oh, sorry, this is not horizontal. Sorry. This is vertical. Let me redraw again. Okay, horizontal is like this. Okay, is like this, horizontal. Okay, and in this case, current is moving cross here and a dot here. Okay, so at which part of the graph where the moment will be the greatest? Yi-Ting, well done. How about the rest of you? Which part of the graph will you show? Uh, Hello, nobody answering question number B then. Then I got no time to go through some practical tips. Okay, Ryan, one of your answer for part 2 is correct. Oscar, you must explain what changed. Okay, you must explain what changed. Okay, Hao-Rui, your part 1 is correct. Okay, Oscar, your number 1, you must explain your answer. Does it increase or decrease? Okay, your number 2 is correct. Okay, number 2 is correct. Okay, the rest of you, what is your answer? Okay, Yiting, your part B2 is correct. Well done. Oscar, your number 1 is correct. Very good. And Pei Kwan, you're explaining for which one? What are you explaining for? I don't understand. Pei Kwan, I don't understand. I understand your answer, your statement, but you're not answering the question. Okay, Hao Rui, yes. The time taken, there's another word, there's another scientific word for it. So what is it? Okay, so first of all, when it's horizontal, do you remember just now you mentioned? When it's horizontal, this is the pivot. The perpendicular distance is the greatest. Okay, so your H will be at the highest point. Any of these points will be your horizontal point. Okay, when it's 0, it is your vertical point. Is that clear? Okay, that's for part B, part 1. Then when you increase your battery, okay, what happened? When you increase your EMF, your current go up, okay, your force will increase as well. So what you will see in the graph is your amplitude will go up. Okay, the amplitude will go up. Okay, so you must say that the amplitude of the moment will increase. Okay, but because it turned faster, okay, the time taken will be shorter as well. So you must write down the period of the wave, okay, decreases. Is that clear? So in your graph, you'll look something like this. You'll be higher, 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 higher. Clear? Okay, if you are okay with this, we go to the last question. Okay. If you are okay, give me a yes reaction, everyone. Let's go to the one last question, 2018. No, not 18. Okay, last 2 questions. Okay, let's do this quickly. Pei Kwan, can you try to do A part 1? Then the rest of you quickly explain part 2. Okay, part 2 and part B. Okay, quickly explain part 2 and part B. Pei Kwan, you try do question number A. Do on the screen. Bei Kwan, the magnetic force don't need to draw. Okay, let me erase for you. This part no need to draw. Okay, so let me check. Okay, very good. Part A, correct. So the rest of you do part 2 and okay, I'll give you the answer of part 2 because everything is all very similar. All very similar. Okay, so using Fleming left hand rule. Okay, spell it out in the exam. Okay, in this case, because it's 2 mark, then you explain clearer. Okay, explain clearly. Explain clearly about. Okay. So must say that the index, the left index finger points in the direction of the north-south magnetic field. Okay, the left middle finger points in the direction of the current. So the direction that the thumb is pointing tell us the direction of the force. Okay? Okay, this one is actually I did not ask you to write because I think by now you all should know. Okay, now do part B. So as you rotate around the axle and a split ring commutator ensures that the okay, for part B also, I don't think I need to explain because I already explained that before. Let's do the last question quickly. Then I'll give you a very quick summary of. Okay, can I move on with this? Okay, Oscar, your direction is wrong. Can you check again? Using your, you mentioned that on the on the AB side upwards, that is wrong. Can you try again? Can you try again before I move on? Ryan, the thumb doesn't indicate the magnitude of the force. The thumb indicate the direction of the force. Okay, not the magnitude. Okay, you must change that. The exam, you cannot tell me typo one. Okay, Oscar, you understand now? Let's go to the last question. Okay. Let me see. Okay, this question is for the next part, electromagnetic induction. Okay, we'll skip this question now because it's on magnetic induction. Okay, this is not a motor. This is the opposite, where you're using force to produce electricity. Okay, so let me just say a bit of things about practical. Okay, if you have not learned your theory, okay, don't worry. Physics practical, there's nothing to memorize. Okay, unlike chemistry, where you must memorize certain reactions, certain color change, and so on. Physics, you need to actually know your steps. Okay, follow the instruction, do everything according to the direction. Okay, and basically in physics, you just need to follow direction. You must need to know how to take reading. Okay, number 2, present your data. Okay, number 3, okay, then you have analyze your data. And then number 4, you have a conclusion. Okay, and in the conclusion, you also must know your errors. Okay, what kind of errors are there in your practical? Okay, so for taking reading, you must understand that your data is not more accurate than your equipment. Okay, so when you present your data, okay, then when you present your data, usually it's in a table. Okay, in your table, then you draw your graph. Okay, so as you can see, a lot of physics practical, you don't need to know your theory one. They will not ask you your theory question. It's about testing whether you know the process. Okay, so when you take reading, for example, if you are using a meter rule to take a reading, and you know the meter rule is accurate up to 0.1 cm or 1 mm, your reading cannot be more precise than this value. So in your table, it should be accurate to your equipment precision. Number 1. Is that clear? Okay, so when you draw your table and present your data, okay, the data, raw data from your experiment, okay, talking about from your experiment, it shouldn't be more precise than your equipment. So you must see your equipment is how precise it can go. Okay, how precise it can go, and then you present the data. Okay? Then, after you present your data, you need to do some calculation. So for example, right, your data, you have header. So for example, your header, like in this case, length. Always write down the unit. Write down the unit. And then in your table, okay, in your table, there will be no unit in your table. So this is your raw data. Okay, raw data. So maybe you got L1, maybe you got L2. Okay, so you did your 2 data. Then finally you have your average. Okay, so this average here that I'm talking about is your calculated value. Okay, I must repeat. Your calculated value cannot be more precise than your raw data. Okay, I give an example. Let me go to the next page. I'll give you an example. And this is what I've always been sharing with you in your in your calculation, which is the same theory. Okay, so for example, if I use a meter rule to measure your height as 1.73 meter, then this is your height. Then your shoe sole, I use a vernier caliper to measure. Okay, maybe I measure it, sorry, 173.732. Then I use the shoe sole, I measure it as 2.45 cm using a vernier caliper. Okay, so let me just change this to cm first. So what will be the total height? You need to add these 2 together. So for addition and subtraction, okay, this is what asking me. For addition and subtraction, you use the least dp. Okay, use the least dp. I repeat, for addition or subtraction, you use dp. So in this case, this is 1 dp, this is 2 dp. Okay, your final answer cannot be more accurate than 1 dp. Am I right? Because you're using a meter rule, your height can be 173.22. It can be 173.18. But because the meter rule can only measure up to 0.1 cm, okay, can only measure up to 0.1 cm. Therefore, your final answer cannot be so accurate. Yes, add together you get 175.65. But because the second digit here you do not know, so you cannot present answer as 175.65. Your final answer here should be also 1 dp. Okay, you understand this idea? So your final answer here will be 175.7. Is that clear? Is that clear about this? So for addition and subtraction, you choose the least dp. Then for multiplication or division or even power, anything that's not plus or minus, you use the least SF. Okay, so for example, 4.3 Newton multiplied by 3.22 cm. Okay, what would your answer here be? Can all of you try? Your unit will be Newton cm. Can all of you try? What will your answer be for this? Everyone? Okay, what will the answer be for this? For this, I will give you a clue. This is 2SF because it's multiplied. This is 3SF. So your final answer here should be 2SF. Okay, all of you tell me the answer. Oscar, well done. Yiting, well done. Howry, well done. Beikwan, well done. How about the rest of you? Okay, so in this case, it should be 14. Is that clear? Okay, so this apply very important for your table. How much SF and how much DP to use. So when you need to plus or minus, you use the DP. If you need to multiply or divide, you use the SF. Okay, one exception, if you have a constant. Okay, constant, for example, like pi. Pi is a constant, right? Or you use the G. G is a constant. G is like 9.81 something. Okay, pi is 3.14 something. Okay, this one you ignore. You don't go and use the pi as your SF. So for example, you want to find the area of a circle. Okay, so your radius is, let's say, 3.4 cm. So what is your area? So you know your pi is 3.14, right? Okay, this one you ignore. You just use your radius, which is 2SF, because you multiply, your final answer will be just 2SF. You ignore your constant. So for constant, you don't take into account. Okay, don't take into account, just leave it there. Okay, so just use whatever experimental data. Use the SF or DP to calculate. Is that clear? Okay, this point, if you are okay, give me a thumbs up. Okay, next point. Okay, then they also like to tell you to draw graph. If the graph happen to be cutting through 0, let's say this is variable A, variable B. So you say that A and B are directly proportional. Okay, so make sure when you plot, they are roughly the same number of points above and below. Okay. So when you have a straight line cutting through zero, okay, cutting through zero, they are directly proportional. Okay, when it's very close to zero, means that your drawing not very good or your experiment not so well. Then most likely also should cut through zero. Then you go and see whether any of the experiment you can redo that 1 or 2 point so that you can force it to zero. Okay, if it's very close to zero, means that likely it should be cutting through zero. Then if it's not cutting through zero, okay, C and D. So you can see that C and D are, what's the relationship? Linearly related. Okay, so in this case, this is C and D is linearly related. Is that clear? Can? And then when you draw your graph, you must also do your scale. Okay, your scale. Your scale, you don't go and do 1:3 cm. Use 2, use 1, 2, 5, 10. Okay, use multiple of 1, 2, okay, 5, and 10, and so on. Don't go and use 3. Don't go and use 4. Don't go and use 6, 7. Okay, these are odd kind of scale. Okay, so you use like 1 cm represent 1 Newton, or 2 Newton, or 5 Newton, or 10 Newton, and so on. Don't use 3. Don't use 7. Okay, use this type of scale. Clear so far? Then a lot of times you also require to calculate the gradient. Okay, gradient. So make sure your gradient is as big as possible. So this blue is okay. Don't go and do this. This is no good. Too small. So make sure when you count your gradient, you try to draw as big as possible. Your graph, okay, in exam, your graph, both your x and y axis must be greater. I mean, not the axis, your graph on the horizontal and the vertical must be greater than half of your graph paper. What do I mean by this? If this is your graph paper, right? Okay, then you draw your graph. But it's like this. So this is less than half. Teacher don't like. So you need to choose a scale so that when you draw your graph, this part is more than half of the whole height of your graph. Is that clear? Okay, so your graph, okay, from bottom to up must be more than half of your graph. From left to right must be also more than half of your graph. Okay, I have a question here. By Hao Rui, must the graph starts from 0? No need. But if you want to see whether it is directly proportional, then you should start from 0 on both axes. Because if you don't start from 0, you can't tell whether does it cut through 0. So you must look at your data point. Is it like very, very, very far from 0? If it's very, very far from 0, you will never hit 0, then no need to start from 0. But if you know that your graph is going to cut through 0, a very good chance it's going to cut through 0, then better cut through 0, so that you can explain that, you can conclude that the two variables are directly proportional. Okay, so the thing you must know is gradient is m, which is b over a, okay, which is b over a, is change of b over change of a. So you should know, right? Or change of y over change of x. Okay, so you must know how to count the gradient. Same thing, gradient, because division, you choose the least SF. Or basically, in your calculation, you can use the most accurate answer, but your final answer should be the least SF. You understand what I mean? Don't use the least SF on top, least SF below. You use the most accurate answer, go and count. Your final answer should be based on the least SF. Clear? Okay, so Harry asked me a question, my graph start from 0, I will answer. Okay, then finally, error. What kind of errors must you do? Okay, so to remove random error, meaning error that can be randomly occur, you repeat your experiment a few times and take the average. Okay, for equipment error, like 0 error, you need to take into account the biasness, okay, of the error. All right. Any question for me regarding practical? Okay, just don't need to worry so much. Practical is about skill. It's not about knowledge. Okay, knowledge will be tested in your paper 1 and 2. Okay, in practical, they will not ask you whether light, what's the speed heat, what's the value and what's the theory between this and this. But if you know your theory is actually a bit better, because your conclusion, you can use your theory, your knowledge of theory to verify whether your experiment is correct or wrong. Okay, so knowing your theory helps but it's not necessary. Because when we do experiment in physics, it's just like you're a scientist. You do experiment because you want to verify a certain hypothesis, a certain theory. So you do not know a theory. That's why you do experiment to find pattern. And from the pattern, you can conclude whether does it fit the theory or not. Okay, that's the main purpose of physics experiment. Ken, any more question for me? If there's a question for me, give me a yes reaction. If there's no question for me, give me a no reaction. Ryan, you got what question for me? Ray, anything for me? Ryan, you got question for me? How to do planning? Planning of what? Ray? Yeah, okay, Ray asked me how to do planning. So can you tell me, you want me to plan for what? Plan for drawing the table or plan for drawing the graph? The planning task, usually they will not ask you to plan, but they'll give you instruction, you follow, then you record down the data. Then from the data, you need to go and calculate certain things, calculate gradient, then give conclusion. So planning, usually there's not much planning need to be done. But if it's planning, just be as detailed as possible. Okay, Ryan asked a question. For drawing of table, if need find L or I, do I need to include a column for Ryan? Can you type out the question in for everybody? Because I had to speak your question. I also don't understand your question. Can you type out to show everyone? Ryan, can you type out your question and show everybody? I don't understand what's your question. If I draw a table, okay, then what do you want to ask? So for example, length. So your independent variable will be something like this: 1.0, 2.0, 3.0, 4.0. So this one you set. Okay, because of the length, you need to measure your current. Okay, then maybe your current based on your ammeter. Okay, so what do you want to ask next? I don't understand your question, right? What do you mean by 1 over L and 1 over I? I don't understand what you need, what you're asking me. But if there's a need to find the inverse, you can also put the inverse. So you can put like 1 over L, which is Cm minus 1. Okay, if there's a need to because of your formula or equation or what the paper asks you, you can also do that in your table. Then you just extend your table, extend, and add whatever you need to add. Okay, I still don't understand your question now, Ryan, but did I answer your question? Okay, for pendulum, okay, can you type to everybody? For pendulum experiment, are you supposed to start the timer once you release at the top or when it passes the lowest point in the middle? Okay, for pendulum experiment, okay, this is one oscillation, correct? At which time, my question is this, Haore, at which time is the pendulum moving the slowest? At point A or point B? At which time would the pendulum be at the slowest speed? Okay, so it'll be at the slowest speed at A. Okay, but first of all, when you start at A, you let go, you don't start immediately. You let it swing for 2 or 3 oscillation. Then when you go back to A again, then you start. Understand, Haore? Because at the lowest point is moving at the fastest, so it's not easy to determine when it passed the middle point because it's moving at the fastest speed. So for pendulum experiment, start at A, but when you let go, you let it swing a few oscillation first. And then for pendulum experiment, this angle, try to make it as little as possible. Okay, less than 5 degrees. Okay, don't go and put it far away and let go. You just displace a bit. Let go, let it swing 2, 3 times, then you start counting. Is that clear? How did I answer your question? Okay, Ryan asked me, Ryan, can you type for everybody? Don't just show to me. Okay, Ryan asked for oscillation. Can we just do 5? Normally you do at least 10, ideally 20. Don't do 5 because 5 is too little to factor in all your reaction time and so on. So do more. Okay, do more. Okay, any more question for me? Okay, so before you go, give me 2 value. Okay, first value 1 to 10 on electromagnetism, 1 to 10 on practical. Tell me how much have I value add to you? Okay, once I call your name, you may go. Give me 2 value. How much have I value add to the electromagnetism part, and how much have I value add to you in practical? Okay, thank you, Oscar. Thank you, Ryan. Thank you, Chelsea. Thank you, Aure. Thank you, Yiting. Good night. Guan, how about you? How are you? Okay. Thank you, Guan. Good night. Goodbye.